Okay, for each function, identify the points of discontinuity. And for this right here, for points of discontinuity, I want you to think vertical asymptotes, horizontal asymptote, and the domain. Then you're going to sketch the graph. That sounds pretty complicated, but you're going to find that it's not too much. So here we have f of x is equal to 3 over x subtract 1. Well, sorry, I was sneezing. It's the parent function of this function right here is just 1 over x. So remember, to find a vertical asymptote, because that's one of your tasks, is a vertical asymptote is formed when you've got a bunch of stuff, and if the denominator is 0, whatever zeroes out the denominator. So if you had a bunch of stuff and you had x plus 3, where x is equal to negative 3, there would be a vertical asymptote, because negative 3 zeroes out. If you just have an x right there, well, where x is equal to 0, there would be a vertical asymptote. So remember, the graph of the parent graph of this rational function is it looks like this, which means the asymptotes, the vertical asymptote, is where x is equal to 0. And where there's a vertical asymptote, there will also be a discontinuity. And then notice there's also a horizontal asymptote, and I'll show you how to find those in just a minute. So we have our 3 over x minus 1, and what I've done here is I've drawn the original graph like I did right here, and notice where there's a vertical asymptote, it's where x is equal to 0, that's the equation. Where there's a horizontal asymptote, right here, it's where y is equal to 0, that's also the equation. And notice the vertical asymptote and the discontinuity equation is the same. And then I also show you what the domain is. So this graph is continuous. Here, let me choose a different color. Starting from this direction, going all the way up almost till you touch to 0. So from negative infinity up until 0, and notice both of these have the open brackets. It's because neither one of those are touched. And then the graph starts from here, almost where it touches 0, and it goes that direction on to positive infinity. All right. So we have to take this graph right here, and we have to do some things with it. I'm trying to think if I did that below. I did. All right. So imagine this is in the parentheses. So what zeroes out x now? Well, what's the opposite of negative 1? Positive 1. And nothing really has changed. 1 over x. So here's how you find the horizontal asymptotes. Here's the guide. When the x value in the numerator is lower than the x value in the denominator, you're going to have a horizontal asymptote at y is equal to 0. Well, look at what we had. 3 over x minus 1. Imagine that is x to the 0, because x to the 0 is 1. 1 times 3 is 3. So when you ever see a constant by itself, you could imagine an x to the 0. Well, this is x to the first. Notice this is lower, x to the 0 is lower than x to the first. So we have a y is equal to 0. So for this right here, our horizontal asymptote will be y is equal to 0. And then notice this 3 in the numerator, well, that just means the same as 3 times 1 over x minus 1. So that multiplier of 3 means 3 times as steep. And let's see if I regraphed it. I didn't, so we're going to graph it right here. This whole graph right here, the x value got moved over positive 1. So we're going to take this whole thing and we're going to move it. Whoops. I'm going to see if I can. that work? It did not. There we go. Okay, that works. So now we've moved over. Notice the vertical asymptote moved also. The vertical asymptote right there also moved over. But now what we're going to have to do is multiply everything by that multiplier of 3. So at this point right here, 3 times 1 is up here at 3. And down here, 3 times -1, down here at -3. And that new graph is going to curve. It's going to get steeper much more quickly. And that would be the new graph. And notice this domain and range now, because where the vertical asymptote is at 1, so that makes writing the domain pretty easy. So now the discontinuity is at 1, so we're going to go from, whoops, negative, I just drew that strangely, negative infinity up to 1, we're not going to be touching 1, and then from 1 to positive infinity. And that's what happened right here. This graph now is getting really, really close to 1. And starting here, from really, really close to 1 on to positive infinity. Just like that. All right, and let's see if I did any others. Oh, okay, so I need to finish the horizontal asymptote guide. So notice if you had a polynomial with the lead exponent in the numerator and the denominator the same, well, you're going to have a horizontal at y is equal to the fraction of a divided by b. Let me give you an example. If we had 2x squared minus 3x plus 5 over 3x squared plus 4x minus 12, the horizontal asymptote would be where y is equal to 2/3. So when the lead exponents in the polynomial in the numerator and the denominator are the same, whatever the a and the b are, that's where that ratio right there that's formed, that's where the horizontal asymptote will be. All right, and then when you've got an x, say 2, the exponent is 2 values higher than, or 2 degrees lower. So this is what I mean. If you have x to the 4th and a bunch of stuff over x squared and a bunch of stuff, or x third over x to the 1st and a bunch of stuff, you're just going to ignore x fourth over x squared. You're going to end up with this quadratic. And so there really won't be, you're just going to treat it like, oh, I just have this quadratic equation now, because when you do long division, that's essentially what you're going to end up with. So there will not be a horizontal asymptote. And then there's one other. If you have x to the 2nd over x to the 1st, it's just 1 degree higher. So x cubed over x second. Well, that's where you're going to end up with a slant asymptote, and we'll get to that later. And that's where you have to do long division to figure out the line of the slant and then graph it that way. All right, that is it for finding points of discontinuity for vertical asymptotes, horizontal asymptotes, and the domain of a graph, of rational graphs specifically.